There are galaxies in our universe that, according to everything we understand about cosmic time, simply shouldn't exist yet. The James Webb Space Telescope has been quietly peering into the deepest reaches of space, looking back nearly to the very beginning of everything, and what it found there has left astronomers gently puzzling over something extraordinary. These are massive, fully formed galaxies appearing just a few 100 million years after the Big Bang, a cosmic eye blink when galaxies should barely be taking their first tentative steps toward formation. Tonight, we'll explore this quiet mystery step by step, using real observations, the patient physics of starbirth, and the delicate dance of matter that shapes our cosmos across deep time. It's a story of light traveling impossible distances, time stretching beyond imagination, and the universe revealing secrets we thought we'd never glimpse. If this gentle journey through cosmic mysteries helps you drift toward understanding or peaceful rest, your quiet like, your soft subscription, and any thoughts you share mean more than you know. Now, let's begin this exploration together, without any rush. Hello there and welcome to Science for Sleep, where we explore the universe's most fascinating mysteries at a pace that soothes rather than startles. Have you ever wondered what it might feel like to discover something that completely changes everything you thought you knew about reality? Tonight, as you settle into whatever comfortable space you've chosen for this gentle journey, whether it's your favourite chair, a cosy bed, or perhaps somewhere quiet where the day's concerns can slowly drift away, we're going to explore one of the most extraordinary discoveries in the history of astronomy. What would you think if I told you that the most powerful telescope humanity has ever built just spotted galaxies that, according to our best understanding of physics and cosmic evolution, simply should not exist? Yet, before we begin this unhurried exploration together, if these calm journeys through cosmic wonder bring you peace or spark gentle curiosity about our universe, your soft tap on subscribe and any thoughts you might share mean more to me than you know, helping create a community of people who find comfort in the vastness and mystery of space. Take a moment to notice your breathing, perhaps glance around your current surroundings and let yourself settle into this contemplative space we're creating together. Tonight we're not rushing toward any destination, but rather allowing ourselves to drift thoughtfully through a discovery so profound that astronomers are calling it paradigm shifting. What exactly did the James Webb Space Telescope find lurking in the deepest reaches of space and time? How can galaxies exist in places where cosmic history suggests they should be impossible? These questions have been keeping scientists awake at night, not from worry but from the kind of intellectual excitement that comes when the universe reveals secrets we never expected to glimpse. The story we're about to unfold together moves gently from the familiar experience of looking up at tonight's stars to the mind-bending revelation that some of those distant lights are showing us glimpses of cosmic architecture that challenges everything we thought we understood about how the universe grew from its earliest moments into the intricate tapestry of galaxies we see today. We'll discover together how light itself becomes a messenger from the deepest past, carrying information across billions of years of cosmic expansion to reach our eyes and instruments here on Earth. There's something deeply comforting about knowing that the photons entering your eyes when you look at distant stars tonight began their journey long before our planet even existed, travelling patiently through the expanding cosmos to arrive at just the right moment for you to see them. As we explore these impossible galaxies, we'll encounter three remarkable discoveries that each tell a different part of this cosmic puzzle, starting with 6 massive ancient galaxies that appeared when the universe was barely more than an infant, continuing with 3 enormous star-forming monsters that earned their nickname from their distinctive red appearance in Webb's infrared vision, and concluding with the astounding revelation that thousands of galaxies resembling our own Milky Way were thriving in cosmic epochs when such delicate spiral structures should have been impossible to maintain. Each discovery adds another layer to our growing understanding that the early universe was far more active, organised, and capable of rapid galaxy formation than decades of careful theoretical work had predicted. What makes these findings particularly fascinating is not just their implications for cosmic evolution, but the way they demonstrate science's beautiful capacity for self-correction and growth when new observations challenge existing models. Tonight we're going to take our time with these concepts, returning to key ideas multiple times with deepening understanding, using analogies from everyday experience to make the vastness of cosmic time and space feel more accessible and personally meaningful. There's no need to grasp everything immediately, or feel any pressure to solve these cosmic puzzles yourself. Instead, we can simply allow ourselves to be carried along by the wonder of discovery and the quiet satisfaction that comes from learning something new about our place in this remarkable universe. So whether you're listening as preparation for sleep, as gentle companion to evening activities, or simply because you find comfort in contemplating the cosmos, let's begin this patient exploration of galaxies that shouldn't exist yet. Somehow do, carrying with us the understanding that some of the most beautiful discoveries come not from confirming what we expect, but from being surprised by reality's capacity to exceed our imagination. What happens when the universe decides to completely ignore the rules we thought governed cosmic evolution? As we continue settling into this gentle exploration together, let me share what makes tonight's journey particularly special and perhaps surprisingly comforting despite dealing with concepts that have left astronomers scratching their heads in wonder. The puzzle we're about to unravel isn't one of those intimidating scientific mysteries that requires advanced mathematics or years of specialized study to appreciate. Instead, it's the kind of cosmic detective story that reveals its secrets through patient observation and careful thinking about what we're actually seeing when we peer into the deepest reaches of space and time. Think of tonight's exploration as a slow walk through a cosmic art gallery where each discovery is a masterpiece that shouldn't exist according to everything we thought we knew about how the universe creates its most magnificent structures. What we're discovering together won't overwhelm you with technical jargon or complex equations. Rather, we'll build understanding step by gentle step, using familiar experiences and everyday analogies to make even the most mind-bending concepts feel accessible and personally meaningful. The beauty of these recent discoveries lies not in their complexity, but in their profound simplicity. They're showing us galaxies that appear exactly where and when our best theories suggest such objects should be absolutely impossible to find. Imagine walking into your garden expecting to see seedlings, and instead finding fully mature oak trees that somehow grew to towering heights overnight. This captures something of the amazement astronomers experienced when Webb's first deep images revealed massive, complex galaxies existing just a few 100 million years after the Big Bang, when cosmic evolution should have barely begun its work. Tonight we'll move naturally from concepts you already understand intuitively, like how light takes time to travel from distant objects to your eyes, gradually expanding that foundation to encompass the revolutionary discoveries that are reshaping our understanding of cosmic history. There's something deeply satisfying about learning that the universe is far more creative and capable than we previously imagined, suggesting that even in its earliest epochs, cosmic forces were capable of assembling magnificent galactic structures with surprising efficiency and elegance. The three major discoveries we'll explore together each tell a different chapter of this unfolding story, revealing how Webb's unprecedented infrared vision has unveiled hidden populations of ancient galaxies that challenge fundamental assumptions about cosmic timeline and galactic formation processes. What makes these findings particularly remarkable is their consistency. This isn't a case of one unusual object that might be explained away as an anomaly. Instead, we're seeing multiple independent lines of evidence all pointing toward the same revolutionary conclusion that the early universe was far more active and sophisticated than decades of theoretical modelling had predicted. As we journey through these discoveries, we'll encounter galaxies that formed stars at impossible rates, massive spiral structures that survived in environments where they should have been torn apart, and ancient stellar populations that suggest cosmic evolution proceeded far more rapidly than previously thought possible. The wonderful thing about approaching these concepts gradually is that each new understanding builds naturally on what came before, creating a growing appreciation for both the elegance of cosmic processes and the remarkable capability of human ingenuity in developing instruments sensitive enough to capture light that has been travelling toward us since the universe was less than 1/10 its current age. What emerges from the observations isn't chaos or confusion, but rather a richer, more nuanced understanding of how gravity, gas dynamics, and stellar formation can work together under primordial conditions to create galactic masterpieces far earlier in cosmic history than anyone anticipated. Tonight's exploration celebrates the beautiful interplay between human curiosity and cosmic revelation, showing how our species' drive to understand the universe continues yielding discoveries that expand our sense of wonder rather than diminishing it. There's no examination at the end of our journey, no complicated formulas to memorize, no pressure to become an expert in galactic evolution. Instead, we're simply sharing in the joy of discovery and allowing ourselves to be amazed by a universe that consistently exceeds our expectations in the most delightful ways. The concepts we'll encounter may stretch your imagination, but they'll do so gently, inviting you to consider possibilities that are both scientifically rigorous and profoundly inspiring. Each galaxy we discuss represents not just an astronomical object, but a testament to the universe's remarkable capacity for creating beauty and complexity under conditions we're only beginning to understand. So as we prepare to dive deeper into these cosmic mysteries, carry with you the reassuring knowledge that understanding comes naturally when we approach complex topics with patience, curiosity, and the willingness to be surprised by reality's infinite capacity for wonder. Have you ever noticed how the most profound revelations often come in groups of three, like acts in a play that build toward an unexpected climax? Tonight we'll discover together three interconnected astronomical revelations that have fundamentally altered our understanding of cosmic evolution, each more astonishing than the last, creating a symphony of evidence that the early universe was capable of architectural feats we never imagined possible. Our first act introduces 6 colossal galactic structures that astronomers initially dismissed as impossible. Massive stellar cities containing hundreds of billions of stars existing when cosmic theory insisted such complexity should require billions of additional years to develop. These ancient leviathans appeared in Webb's images like unexpected guests at a party, forcing scientists to completely reconsider their assumptions about how quickly gravity can assemble matter into organized galactic communities. Moving into our second revelation, we'll encounter 3 spectacular objects nicknamed the Red Monsters, dusty galactic giants that were converting raw cosmic material into stars with efficiency rates that shatter every model of stellar formation physics, operating like cosmic factories running at productivity levels that should be theoretically impossible under primordial conditions. Finally, our third discovery unveils perhaps the most mind-bending finding of all: thousands upon thousands of spiral galaxies, resembling our own Milky Way thriving in cosmic epochs, when violent mergers and chaotic conditions should have destroyed such delicate architectural masterpieces before they could establish their graceful spiral arms. What makes these discoveries particularly fascinating is how they complement each other, creating multiple independent lines of evidence that all point toward the same revolutionary conclusion about early cosmic productivity. As we explore these findings together, we'll begin each concept with experiences you encounter daily, building bridges between the familiar rhythms of earthly existence and the extraordinary processes operating on galactic scales across billions of years. Think about how water flows from your faucet, how bread rises in your oven, or how gardens grow from seeds. These everyday transformations will serve as stepping stones toward understanding how cosmic gas collapses into stellar nurseries, and how those nascent stars organize themselves into the magnificent spiral patterns we observe in distant galaxies. The beautiful thing about learning cosmic concepts through familiar analogies is how it makes the vastness of space and time feel personally accessible rather than intimidatingly abstract. We'll discover together how understanding galaxy formation is remarkably similar to watching a city develop over decades, with infrastructure appearing first, followed by neighborhoods, then complex transportation networks that connect everything into a functioning metropolitan area. Throughout our exploration, we'll return repeatedly to core concepts, each time adding new layers of understanding that deepen, rather than complicate our appreciation for these cosmic processes. This circular approach to learning mirrors how scientists themselves build understanding, starting with basic observations, developing theories, then testing those models against new data that often reveals unexpected complexities requiring further refinement. What emerges from this patient, iterative process isn't confusion, but rather a richer, more nuanced picture of how the universe operates on scales ranging from individual star formation to the assembly of entire galactic superclusters. The journey we're taking together values comprehension over completion, meaning there's no rush to cover every detail or solve every mystery we encounter. Instead, we can allow ourselves to marinate in wonder, savoring the elegant solutions nature has developed for organizing matter and energy across cosmic timescales that dwarf human experience. Each galaxy we discuss represents not just a collection of stars, but evidence of processes so fundamental that they shape the very environment in which planets like Earth could eventually form and support the development of life capable of contemplating its own cosmic origins. As we move through these discoveries, you'll notice how certain themes emerge repeatedly, like musical motifs in a symphony, reinforcing key insights about cosmic evolution while revealing new harmonies between different aspects of galactic development. The repetition isn't redundancy, but rather the natural way complex understanding develops, with each encounter deepening appreciation for the elegant interconnectedness of cosmic processes. What makes this approach particularly satisfying is how it mirrors the actual process of scientific discovery, where breakthrough insights rarely arrive as sudden revelations, but instead emerge gradually through patient accumulation of evidence and careful consideration of what that evidence might mean for our broader understanding of natural processes. Tonight's exploration celebrates both the magnificent creativity of cosmic evolution and the remarkable ingenuity of human minds capable of developing instruments sensitive enough to capture photons that have been travelling since the universe was barely more than a cosmic infant. The tools and techniques that revealed these impossible galaxies represent centuries of cumulative human achievement in optics, engineering, and theoretical physics, all focused on satisfying our species' fundamental drive to understand our place in the cosmos and the processes that shape the universe we inhabit. What if every photon entering your eyes right now carried a personal message from the past, like countless tiny time capsules delivering news from moments that have already slipped away into history? When you gaze at the moon tonight, something remarkable is happening that most people never consider. You're not seeing the moon as it exists in this precise instant, but rather as it appeared 1.3 seconds ago when those silvery photons began their journey across the void between lunar surface and your retina. This delay might seem insignificant, barely longer than a heartbeat, yet it represents our first glimpse into the profound truth that light, despite being the fastest phenomenon in the universe, still requires time to traverse even modest cosmic distances. Consider the familiar experience of watching a distant thunderstorm approach. How you always see the brilliant lightning flash several seconds before hearing thunder's rumbling announcement. This everyday observation reveals the fundamental principle that light travels far faster than sound, yet both require measurable time to reach our senses. Similarly, every star visible in tonight's sky is broadcasting its luminous message across vastly greater distances, with photons that departed stellar surfaces years, decades, or even centuries ago finally completing their solitary voyages to arrive at Earth's atmosphere and eventually your eyes. The nearest star beyond our solar system, Proxima Centauri, appears to us as it existed 4 years and 4 months ago, meaning that if this stellar neighbour suddenly exploded tomorrow, we would continue seeing it twinkling peacefully for another 4 years before witnessing the catastrophic event that had already occurred. This temporal displacement becomes even more profound when we consider galaxies millions or billions millions of light years distant, where individual photons have been travelling through expanding space since before our planet existed, carrying visual information from cosmic epochs when the universe itself was radically different from today's mature astronomical landscape. Telescopes function as sophisticated time machines precisely because of this fundamental relationship between distance and light travel duration, allowing astronomers to peer progressively further back into cosmic history by observing increasingly remote objects. When Webb captures images of galaxies 13 billion light-years away, we're literally seeing those stellar congregations as they appeared when the universe was less than 1 billion years old, a cosmic infant compared to today's nearly 14 billion year age cosmos. There's something deeply comforting about recognizing that ancient starlight has been patiently making its way toward us across unimaginable stretches of space and time, as if the universe has been carefully preserving visual records of its own development and gradually delivering them to any civilization capable of building instruments sensitive enough to detect these faint cosmic whispers. Each photon represents an incredibly unlikely success story, having escaped from stellar nuclear furnaces, navigated through interstellar space without being absorbed by gas or dust, survived the stretching effects of cosmic expansion, passed through our atmosphere without scattering, and finally struck telescope mirrors or detector arrays at precisely the right moment to contribute to human understanding of galactic evolution. The photons reaching us tonight from distant galaxies began their journeys when those stellar systems were actively forming new stars, assembling heavy elements through nuclear fusion, and organizing matter into the complex structures that would eventually become the cosmic architecture we observe today. What makes this temporal perspective particularly fascinating is how it allows us to witness cosmic evolution in action, seeing galaxies at different stages of development simply by looking at objects located at varying distances from Earth. Nearby galaxies show us stellar populations that have had billions of years to mature and develop complex chemical compositions, while the most distant observable galaxies reveal raw primordial conditions when hydrogen and helium dominated cosmic chemistry and stellar formation, processes operated under dramatically different environmental conditions. This natural time stratification means that a single Webb observation can simultaneously capture galaxies representing multiple epochs of cosmic history, creating a kind of temporal archaeology where distance serves as a proxy for age and evolutionary stage. Understanding light as messenger transforms our relationship with the night sky from passive observation to active participation in cosmic communication, where each moment spent stargazing connects us directly with events that occurred across the vast timeline of universal development, making us witnesses to the ongoing story of how matter and energy have organized themselves into increasingly complex and beautiful configurations throughout the history of space and time. Have you ever wondered why an ambulance siren changes pitch as it rushes past your location, creating that distinctive drop from high to low frequency that signals the emergency vehicle's passage? This familiar auditory phenomenon holds the key to understanding one of the most profound discoveries in modern astronomy: the realization that our universe is expanding and carrying galaxies away from us at velocities that increase with distance. Picture a balloon covered with tiny dots representing galaxies. As you inflate this balloon, every dot moves away from every other dot with the most distant pairs, separating fastest despite no individual dot actually moving across the balloon's surface. This simple analogy captures the essential nature of cosmic expansion, where space itself stretches between galaxies, carrying them apart without requiring any actual motion through space. Just as the ambulance siren's pitch shifts because sound waves get compressed when approaching and stretched when receding, light waves from distant galaxies undergo similar modifications as they traverse expanding space during their billion-year journeys toward Earth. When space expands during a photon's voyage, the wavelength of that light gets progressively stretched, shifting the electromagnetic signature toward longer, redder wavelengths in a process astronomers call cosmological redshift. Imagine pulling on a rubber band while someone plucks it. The vibrations would produce increasingly lower notes as the material stretches. Similarly, light waves get extended to redder portions of the spectrum as cosmic. Expansion acts upon them throughout their lengthy travels. The most ancient galaxies Webb observes have experienced such extreme redshift that their originally blue and ultraviolet starlight arrives at our telescopes as infrared radiation, completely invisible to human eyes and previous generations of optical instruments. This wavelength transformation explains why Webb's infrared capabilities are absolutely essential for studying the earliest cosmic structures. The telescope literally sees light that has been stretched beyond visible recognition by 13 billion years of universal expansion. What makes this stretching effect particularly remarkable is its uniformity. Every photon from a given distant galaxy experiences identical redshift, preserving the relative wavelength relationships that allow astronomers to identify specific atomic signatures and determine physical conditions within these ancient stellar systems. The patience required for light to complete these cosmic journeys staggers human comprehension. Individual photons departed their source galaxies when the universe was a fraction of its current size, traveling through gradually expanding space that continuously modified their wavelengths while preserving the essential information about their origins. During these epic voyages, the universe aged dramatically, galaxies evolved and merged, stars lived entire life cycles from birth through death, planetary systems formed and potentially developed life, all while these particular photons maintained their steady progress toward eventual detection by human instruments. The expansion rate itself varies throughout cosmic history, initially very rapid during the universe's inflationary epoch, then gradually decelerating as matter's gravitational influence dominated, and finally accelerating again in recent cosmic time due to mysterious dark energy that permeates space. This changing expansion history leaves subtle signatures in the redshift patterns of distant galaxies allowing cosmologists to reconstruct the universe's developmental timeline and investigate the fundamental forces that shaped cosmic evolution. Webb's exquisite sensitivity at infrared wavelengths enables detection of galaxies so distant that their light has been stretched by factors of 10 or more, transforming brilliant blue stellar radiation into the deep red and near-infrared emissions that characterize the telescope's most spectacular discoveries. The redshift measurements of these primordial galaxies reveal not just their distances, but also their ages, chemical compositions, star formation rates, and physical sizes, creating detailed portraits of cosmic conditions during the universe's earliest epochs. What emerges from these redshift studies is a dynamic picture of cosmic development where galaxy formation began much earlier and proceeded far more rapidly than theoretical models predicted, suggesting that the physical processes governing stellar assembly operated with greater efficiency under primordial conditions. The beautiful irony of redshift is that this stretching of light, which initially seems to obscure ancient galaxies by pushing their emissions beyond visible detection, actually provides the very mechanism that preserves information about cosmic history and delivers it to instruments capable of infrared observation. Each redshifted photon carries within its modified wavelength a precise record of how much the universe expanded during that particular light ray's journey, creating a cosmic timeline that allows astronomers to measure both distance and age simultaneously through careful spectroscopic analysis of these ancient electromagnetic messengers. What would it feel like to exist in a universe completely devoid of light, where no stars had yet ignited and no galaxies had begun their slow dance of formation across the cosmic void? For approximately 400 million years after the Big Bang, the universe existed in a state astronomers poetically call the Cosmic Dark Ages, an epoch when space remained utterly black despite being filled with the raw materials that would eventually coalesce into brilliant stellar furnaces and magnificent galactic structures. Imagine moving through a house where electricity has never been installed, where every room remains shrouded in complete darkness, even though all the infrastructure exists to support illumination once power finally arrives and switches get flipped for the very first time. This analogy captures something essential about the early universe's condition. All the necessary ingredients for cosmic illumination were present: hydrogen atoms, helium nuclei, the fundamental forces of physics. Yet no mechanism had yet emerged to transform this primordial material into the luminous beacons we associate with mature cosmic architecture. During these seemingly empty eons, space was actually densely packed with neutral hydrogen gas that formed when the universe had cooled sufficiently for electrons to bind with protons, creating the first stable atoms approximately 380,000 years after the initial cosmic explosion. This neutral hydrogen acted like an incredibly efficient fog bank, absorbing any photons that might have attempted to travel significant distances, ensuring that the universe remained opaque to electromagnetic radiation despite the intense energy that had characterized its violent birth. The temperature gradually decreased as expansion continued, dropping from billions of degrees to merely thousands, then hundreds, finally reaching levels where gravitational attraction could begin competing successfully against the thermal motion that had kept matter dispersed in nearly uniform distributions across cosmic space. What makes this period particularly fascinating is how it represents the universe's transition from a chaotic, energy-dominated state to one where matter could begin organizing itself into increasingly complex structures through the patient accumulation of small gravitational influences acting over vast timescales. The cooling process proceeded with mathematical precision, following physical laws that ensured the universe would eventually reach conditions suitable for stellar ignition, while simultaneously creating the density fluctuations necessary for gravity to amplify into the cosmic web of filaments and voids that characterizes today's large-scale structure. During these dark centuries, invisible processes were establishing the foundation for everything that would follow. Dark matter began clustering into gravitational wells that would eventually capture ordinary matter. Tiny variations in density started growing under gravitational amplification, and the stage was being set for the dramatic transformation that would end this lightless epoch. Think about the anticipation that builds before dawn breaks over a landscape, how subtle changes in the atmosphere hint at the approaching sunrise even while darkness still dominates the horizon. Similarly, the universe was gradually approaching conditions where the first protostellar objects could finally overcome the thermal pressure that had prevented gravitational collapse throughout the preceding dark ages. The hydrogen gas that filled space during this period wasn't uniformly distributed, despite appearing nearly smooth. Subtle density variations inherited from quantum fluctuations during cosmic inflation were slowly growing under gravitational influence, creating regions where matter concentration gradually increased above the cosmic average. These overdense regions became the seeds around which the first gravitational structures would eventually form, growing slowly but inexorably as more material fell into their gravitational embrace and began the compression process that would ultimately lead to stellar ignition. What's remarkable about this preparatory period is how it demonstrates the universe's capacity for patient development, spending hundreds of millions of years establishing the precise conditions necessary for the explosive burst of star formation that would follow once gravitational collapse finally overcame thermal resistance. The physics governing this transition involved delicate balances between competing forces, with gravity working to concentrate matter, while thermal pressure and radiation attempted to maintain dispersion, creating a cosmic tension that would eventually resolve in favor of structure formation. As this epoch drew to its close, the universe stood poised on the threshold of one of the most dramatic transitions in cosmic history. The moment when darkness would give way to light, and the first stellar beacons would begin their work of transforming primordial hydrogen into the heavier elements that would eventually enable the formation of planets, solar systems, and ultimately life itself capable of contemplating these ancient processes. What invisible force could be powerful enough to end 400 million years of cosmic darkness by slowly gathering diffuse gas into blazing stellar furnaces that would forever change the universe's character? Throughout those lightless eons we've been exploring, gravity was working with infinite patience, acting like an incredibly gentle but persistent sculptor that could transform the smooth distribution of primordial hydrogen and helium into increasingly concentrated pockets of matter. Imagine watching campfires begin to flicker one by one across a vast wilderness that has never known illumination, each new flame representing a victory over the forces that had maintained cosmic darkness since the universe's birth. The first stellar objects to ignite were nothing like the relatively modest stars we observe in today's mature galaxies. Instead, they were colossal giants containing 30 to 300 times more mass than our Sun, burning with such ferocious intensity that they could illuminate regions of space spanning hundreds of light years. These primordial beacons represented a completely different category of stellar evolution, operating under physical conditions that no longer exist anywhere in the contemporary universe, because the raw materials from which they formed have been forever altered by billions of years of stellar processing. The process of their formation required overcoming enormous obstacles, as the universe lacked the heavy elements that facilitate cooling in modern star-forming regions, forcing gravity to work much harder to compress hydrogen and helium to the densities and temperatures necessary for nuclear fusion to commence. Without carbon, oxygen, silicon, and other heavy elements to radiate heat efficiently, these early stellar nurseries remained much hotter than their modern counterparts, allowing only the most massive gas concentrations to collapse successfully against the intense thermal pressure that resisted gravitational compression. When nuclear fusion finally ignited within these gigantic stellar cores, the result was spectacular beyond imagination, creating luminous powerhouses that shone with the brightness of entire galaxies while consuming their nuclear fuel at rates that would exhaust their energy reserves in just a few million years. This brief lifespan, though seemingly short by human standards, was actually perfectly suited to the universe's needs at that particular epoch, providing just enough time to synthesize heavy elements through nuclear fusion, while avoiding the billions of years that smaller stars require to complete their evolutionary cycles. The death throes of these stellar giants were even more dramatic than their lives, culminating in catastrophic supernova explosions that released more energy in seconds than ordinary stars produce over their entire existences, blasting newly created heavy elements across vast regions of space. These cosmic detonations served as the universe's first heavy element, factories transforming simple hydrogen and helium into carbon, oxygen, nitrogen, silicon, iron, and dozens of other atomic species that would prove essential for forming rocky planets and eventually supporting the complex chemistry necessary for biological processes. The remnants left behind by these stellar explosions were equally transformative, with the most massive examples collapsing into black holes containing tens to hundreds of solar masses, creating gravitational anchors that would eventually serve as assembly points for the first galactic structures. These primordial black holes began immediately attracting surrounding matter, growing steadily as gas and stellar debris fell across their event horizons, establishing the foundation for what would eventually become the supermassive black holes that occupy the centers of virtually every major galaxy in today's universe. The transition from complete darkness to abundant starlight didn't happen instantaneously, but rather unfolded, gradually as more and more gravitational condensations reached the critical mass necessary for stellar ignition, creating an accelerating cascade of illumination that spread across cosmic space like dawn, breaking over an infinite landscape. Each new stellar birth made subsequent star formation easier by enriching the surrounding medium with heavy elements that enhanced cooling efficiency, creating a positive feedback loop that rapidly increased the rate at which new stars could form from available gas reservoirs. The radiation produced by these first-generation stars also began the process of ionizing the hydrogen gas that filled intergalactic space, stripping electrons from atoms and transforming the universe from opaque to transparent for electromagnetic radiation, setting the stage for light to travel freely across cosmic distances for the first time since the universe's earliest moments. What emerged from this epoch was a fundamentally transformed cosmos, where stellar processing had begun the long journey of chemical enrichment that would eventually enable the formation of terrestrial planets, organic molecules, and the intricate biochemical networks that support living organisms capable of studying their own cosmic origins. What happens when decades of careful theoretical modelling meet observational evidence that completely contradicts every prediction astronomers thought they could trust? For generations, scientists had developed increasingly sophisticated computer simulations and mathematical frameworks that painted a clear picture of early cosmic evolution, suggesting that the universe's first galactic structures would be modest, blue-tinted stellar nurseries containing relatively few stars distributed across small volumes of space. These theoretical models, based on fundamental physics and tested against countless observations of nearby galaxies, consistently predicted that cosmic architecture would develop through gradual accumulation processes, requiring billions of years to assemble the massive, complex galactic systems we observe in today's mature universe. The expectation was beautifully logical and mathematically elegant. Young galaxies should appear blue because hot massive stars burn with intense blue light during their brief lifespans, while older galactic populations develop increasingly red coloration as these energetic blue giants exhaust their nuclear fuel and cooler, longer-lived red stars begin dominating the stellar census. According to these well-established principles of galactic evolution, early cosmic structures should display the distinctive blue signature of recent star formation, combined with relatively modest total masses reflecting the limited time available for gravitational assembly processes to concentrate significant amounts of matter into organized stellar systems. The physics underlying these predictions seemed unassailable, based on detailed understanding of how gravity operates on cosmic scales, how gas cooling mechanisms function under different environmental conditions, and how stellar feedback processes regulate the conversion of raw material into luminous stellar populations. Theoretical frameworks consistently suggested that only approximately 20% of available cosmic gas should successfully convert into stars within early galactic systems, with the remaining 80% remaining as diffuse material that would require additional billions of years to participate in stellar formation processes. This relatively low efficiency was expected because young stars produce intense radiation and stellar winds that heat surrounding gas to temperatures where thermal pressure can resist further gravitational collapse, creating a natural regulatory mechanism that prevents runaway star formation from consuming all available material too quickly. The timeline expectations derived from these models were equally clear, suggesting that truly massive galactic structures, comparable to today's largest systems, would require at least several billion years of steady growth through mergers, accretion, and gradual star formation to reach their observed masses and organizational complexity. Previous observational campaigns, conducted with instruments like the Hubble Space Telescope, had generally confirmed these theoretical expectations by revealing populations of small, faint blue galaxies in the deepest available images of distant cosmic regions, reinforcing confidence that scientists understood the fundamental processes governing early galactic development. These careful, methodical observations represented decades of painstaking work by multiple generations of astronomers who pushed technological capabilities to their absolute limits, developing increasingly sensitive detectors and sophisticated analysis techniques to peer ever deeper into cosmic history. The scientific community had developed such confidence in these theoretical frameworks that any significant deviations from predicted evolutionary patterns would require extraordinary evidence and extensive verification to gain acceptance, reflecting the conservative approach that characterizes rigorous scientific methodology. When unexpected discoveries challenge established paradigms, they create simultaneously exhilarating and unsettling experiences for researchers who must balance excitement about potential revolutionary insights against the need to carefully evaluate whether new observations might result from instrumental artifacts, analysis errors, or incomplete understanding of measurement techniques. The beauty of scientific progress lies precisely in this tension between theoretical prediction and observational discovery, where nature repeatedly demonstrates its capacity to surprise even the most carefully constructed human attempts to understand cosmic processes. What makes these surprises particularly valuable is how they force scientists to examine assumptions that may have gone unquestioned for years or decades, leading to deeper understanding of physical principles and more accurate models of how the universe actually operates, rather than how we expect it to behave. The process of reconciling unexpected observations with existing theoretical frameworks often reveals subtle physical effects that had been overlooked or underestimated, enriching our appreciation for the complexity and elegance of natural processes operating on scales far beyond direct human experience. Rather than undermining confidence in scientific methodology, these paradigm-shifting discoveries demonstrate the robustness of approaches that prioritize empirical evidence over theoretical preferences, ensuring that human understanding continues evolving toward increasingly accurate representations of cosmic reality, regardless of how counterintuitive or challenging new findings might initially appear to established scientific consensus. What revolutionary capabilities would humanity's ultimate cosmic detective need to possess in order to peer deeper into space and time than any previous instrument, revealing secrets that had remained hidden since the universe's infancy? The James Webb Space Telescope represents the culmination of decades of engineering innovation and scientific ambition, functioning as our species' most sophisticated time machine capable of capturing electromagnetic radiation that has been travelling toward Earth since cosmic epochs when galaxies were first assembling from primordial gas clouds. Unlike previous space-based observatories that primarily detected visible wavelengths similar to human eyesight, Webb operates exclusively in infrared portions of the electromagnetic spectrum, possessing the unique ability to perceive light that has been stretched by cosmic expansion beyond the range of conventional optical instruments. This infrared sensitivity proves absolutely crucial for studying ancient galactic structures because their original blue and ultraviolet emissions have been redshifted into longer wavelengths during billion-year journeys through expanding space, arriving at our solar system as heat radiation completely invisible to telescopes designed for the visible light detection. The engineering achievements required to create Webb's unprecedented capabilities pushed human technology to its absolute limits, beginning with a primary mirror system containing 18 hexagonal segments that work together to collect electromagnetic radiation across a surface area 15 times larger than Hubble's mirror, providing dramatically enhanced light-gathering power that enables detection of incredibly faint signals from the most distant cosmic objects. This massive mirror assembly folds like origami during launch, then unfurls with mechanical precision once the spacecraft reaches its operational position approximately 1 million miles from Earth at a gravitationally stable location called Lagrange Point 2, where solar and terrestrial gravitational forces balance perfectly to maintain the telescope's position relative to our planet. Webb's location beyond Earth's atmosphere eliminates the atmospheric interference that limits ground-based observations, while its tremendous distance from our planet's heat signature ensures that thermal emissions from Earth cannot contaminate the incredibly sensitive infrared measurements necessary for detecting ancient galactic light. The telescope's revolutionary design includes a tennis court-sized sunshield consisting of 5 ultra-thin layers that block heat and light from the Sun, Earth, and Moon, maintaining Webb's instruments at temperatures approaching absolute zero, where thermal noise cannot overwhelm the faint infrared signals arriving from distant cosmic sources. This sophisticated thermal management system enables Webb to achieve sensitivity levels that surpass previous infrared space telescopes by factors of hundreds or thousands, opening observational windows into cosmic epochs that had remained completely inaccessible to earlier generations of astronomical instruments. Beyond its impressive light-collecting capabilities, Webb possesses field-of-view advantages that revolutionize survey astronomy, capturing images that encompass regions of sky 15 times broader than Hubble's relatively narrow perspective, allowing astronomers to discover rare objects and statistical populations that would require prohibitively long observation times with smaller field instruments. The telescope's advanced spectrographic capabilities enable detailed analysis of light from individual galaxies, revealing chemical compositions, star formation rates, stellar ages, and physical conditions within these ancient systems through careful measurement of absorption and emission lines in their infrared spectra. When Webb's first scientific images were released in July 2022, the astronomical community experienced a collective moment of awe and anticipation, recognizing immediately that decades of theoretical expectations were about to be tested against observational reality with unprecedented precision and depth. These initial observations exceeded even the most optimistic performance predictions, revealing cosmic structures with clarity and detail that surpassed what many scientists had hoped to achieve, while simultaneously hinting at discoveries that would challenge fundamental assumptions about early galactic evolution. The data quality emerging from Webb's instruments demonstrated that humanity had successfully deployed a scientific tool capable of addressing some of cosmology's most profound questions about when and how the first galaxies formed, how quickly they assembled mass, and what physical processes governed their early development during cosmic epochs previously beyond observational reach. Each new image and spectrum transmitted from Webb's position in deep space carries information that took billions of years to reach our instruments, providing direct empirical evidence about cosmic conditions during the universe's youth when physical processes operated under dramatically different environmental circumstances than those characterizing today's mature astronomical landscape. The telescope's remarkable capabilities promise decades of revolutionary discoveries as astronomers continue developing innovative observational strategies that maximize Webb's potential for revealing hidden aspects of cosmic evolution, ensuring that our understanding of galactic formation will continue growing through patient analysis of this unprecedented window into the universe's distant past. What would possess astronomers to point humanity's most expensive scientific instrument at a seemingly unremarkable region of space that previous surveys had deemed utterly ordinary and devoid of interesting phenomena? The Cosmic Evolution Early Release Science Survey, known by its acronym SEERS, represented one of Webb's first systematic investigations into deep cosmic history, targeting a postage stamp-sized section of sky located near the familiar constellation of the Big Dipper that had been observed countless times by the Hubble Space Telescope without revealing anything particularly noteworthy or extraordinary. This patch of celestial real estate had earned a reputation among astronomers as cosmically boring, containing no obvious bright galaxies, dramatic stellar formations, or other eye-catching features that typically attract scientific attention and observational resources. Dr. Erica Nelson from the University of Colorado Boulder was methodically examining Webb's initial SEERS images when she encountered something so unexpected that it initially seemed like an instrumental error or data processing artifact rather than genuine astronomical phenomena. Scattered across the image were several fuzzy reddish dots that appeared far too luminous and massive to exist at the extreme distances their colours suggested, creating an immediate puzzle that challenged everything Nelson understood about early galactic evolution and the capabilities of primitive cosmic structures. Her reaction captured the essence of scientific surprise perfectly when she described the discovery as absolutely bananas, reflecting the profound disconnect between theoretical expectations and observational reality that these mysterious objects represented. The 6 candidate galaxies that emerged from careful analysis of Webb's SEERS data appeared to have formed between 500 and 700 million years after the Big Bang, an epoch when the universe was merely 3 to 5% of its current age, and theoretical models insisted that only small, primitive stellar systems should exist. Each of these ancient galactic structures contained stellar populations comparable in total mass to our modern Milky Way, representing an accumulation of matter that conventional wisdom suggested should require billions of additional years to assemble through gradual gravitational processes. The implications were staggering because these galaxies would have needed to convert raw cosmic material into stars at rates hundreds of times faster than contemporary galactic systems, operating like cosmic factories running at impossible efficiency levels that violated every established model of stellar formation physics. Nelson and her international collaborators spent weeks verifying their measurements and analysis techniques, searching for any possible explanation that might reconcile these observations with existing theoretical frameworks without requiring fundamental revisions to our understanding of cosmic evolution. The team included researchers from the United States, Australia, Denmark, and Spain who'd formed an informal collaboration specifically to investigate Webb's most surprising early discoveries, bringing together complementary expertise in observational astronomy, theoretical modelling, and advanced data analysis techniques. Multiple independent verification attempts consistently confirm the basic characteristics of these mysterious objects, ruling out instrumental artifacts, calibration errors, or analysis mistakes that might have created false signals resembling massive ancient galaxies. The brightness measurements were particularly problematic because they suggested stellar populations that should have been impossible to assemble given the limited time available for gravitational collapse and star formation during the universe's earliest epochs. These objects appeared not only unexpectedly massive, but also surprisingly mature, displaying spectral characteristics that indicated complex stellar populations rather than the simple hydrogen and helium-dominated systems that primordial galaxies should theoretically contain. The discovery process itself highlighted both the power of Webb's capabilities and the conservative nature of scientific methodology, as researchers balanced excitement about potentially revolutionary findings against the need for rigorous verification and peer review before announcing results that might fundamentally alter astronomical understanding. What made these discoveries particularly compelling was their consistency across multiple independent analysis approaches, with different research teams using varying techniques to extract galaxy properties from Webb's infrared data, all arriving at similar conclusions about the enormous masses and ancient ages of these cosmic structures. The fuzzy appearance that initially caught Nelson's attention resulted from these galaxies' extreme distances, which compressed their complex internal structure into barely resolved points of light, even for Webb's unprecedented resolution capabilities. Yet the total luminosity and spectral characteristics provided unmistakable evidence of their true nature as fully formed galactic systems. The scientific community's response reflected the healthy skepticism that characterizes rigorous astronomy, with multiple research groups immediately beginning independent follow-up observations and analysis projects designed to either confirm or refute these extraordinary claims about early galactic evolution and the timeline of cosmic structure formation. How could mature galactic giants possibly exist during cosmic epochs when the universe should barely have had enough time to organize its first tentative stellar experiments? Discovering these massive ancient systems was analogous to walking into what should be a plant nursery filled with seedlings and saplings, only to find towering oak trees with thick trunks, sprawling branches, and fully developed canopies that would normally require centuries of patient growth under ideal conditions. The 6 impossible galaxies challenged every aspect of conventional galactic formation theory because they appeared to contain stellar populations that would have necessitated star formation rates hundreds of times more efficient than anything observed in contemporary cosmic structures. Consider that our own Milky Way, despite being a relatively active galactic system, produces approximately 2 new stars annually from available gas reservoirs, a rate that reflects the complex balance between gravitational collapse, stellar feedback, and thermal regulation that characterizes modern stellar nurseries. These ancient behemoths would have required sustained production rates exceeding several hundred stellar births per year, maintained consistently over hundreds of millions of years, representing productivity levels that seem to violate fundamental physical constraints on how quickly gravity can compress gas into stellar densities. The temporal constraints were equally problematic because these galaxies existed when the universe had completed only 3 to 5% of its total evolutionary timeline, leaving insufficient opportunity for the gradual accretion processes that theoretical models suggested were necessary for assembling such massive stellar congregations. According to established cosmological frameworks, early cosmic structures should have grown through hierarchical assembly, beginning with small protogalactic fragments that gradually merged and accumulated additional material over billions of years through gravitational interactions and steady gas infall from surrounding dark matter halos. This bottom-up construction scenario required patience and extended timescales that simply weren't available during the cosmic epochs when these mysterious galaxies apparently thrived, creating a fundamental contradiction between observational evidence and theoretical predictions about how long galactic assembly processes should require. The chemical composition puzzle added another layer of impossibility to these discoveries. Because massive galaxies typically contain substantial quantities of heavy elements that can only be produced through multiple generations of stellar evolution, nuclear fusion, and supernova explosions that distribute processed material throughout galactic environments. During the universe's first few 100 million years, only hydrogen and helium existed in significant quantities, with trace amounts of lithium representing the sole heavy element legacy from primordial nucleosynthesis during the Big Bang's immediate aftermath. Creating the carbon, oxygen, nitrogen, silicon, iron, and dozens of other atomic species required for forming rocky planets and supporting complex chemistry demanded successive cycles of stellar birth, nuclear burning, explosive death, and chemical enrichment that should have required billions of years to complete. Yet these ancient galaxies displayed spectroscopic signatures suggesting they contained mature stellar populations with chemical abundances that implied extensive processing of primordial material through multiple generations of stellar evolution, presenting an apparent temporal paradox where effects seem to precede their necessary causes. The physical mechanisms that regulate star formation in modern galaxies also seemed inadequate to explain the extreme efficiency these ancient systems would have required to achieve their observed masses so quickly after cosmic dawn. Contemporary stellar nurseries operate under strict regulatory controls where newly formed massive stars produce intense radiation and stellar winds that heat surrounding gas to temperatures where thermal pressure resists further gravitational collapse, creating negative feedback loops that prevent runaway star formation from consuming all available material too rapidly. This self-regulating behavior ensures that galactic systems convert only modest fractions of their total gas content into stars during any given cosmic epoch, preserving fuel for extended periods of steady stellar production, rather than experiencing brief bursts of activity followed by quiescence. For the impossible, galaxies to have achieved their apparent masses, these regulatory mechanisms would have needed to operate with dramatically reduced effectiveness, or perhaps not function at all during primordial cosmic conditions, allowing gravity to work with unprecedented efficiency in converting raw material into luminous stellar populations. The discovery forced astronomers to confront the possibility that their understanding of early cosmic physics might be incomplete, missing crucial processes or underestimating the effectiveness of mechanisms that operated under environmental conditions that no longer exist anywhere in today's mature universe, where billions of years of stellar processing have fundamentally altered the composition and behavior of cosmic gas reservoirs. What happens when revolutionary astronomical discoveries force the entire scientific community to suspend their excitement while meticulously verifying observations that could potentially rewrite fundamental cosmic theories? The initial response from astronomers worldwide demonstrated the beautiful tension between intellectual curiosity and scientific rigor that characterizes how professional astronomy approaches paradigm-shifting claims about cosmic evolution and galactic formation processes. Rather than immediately accepting these impossible galaxies at face value, researchers instinctively applied the methodological skepticism that serves as science's primary defense against wishful thinking, instrumental artifacts, and analysis errors that can create false signals resembling genuine astrophysical phenomena. The first priority involved conducting independent spectroscopic observations that could provide definitive confirmation of these objects' distances and physical characteristics through detailed analysis of their electromagnetic emissions across multiple wavelength bands. Spectroscopy represents astronomy's most powerful diagnostic tool because it reveals the precise wavelengths of light absorbed and emitted by the different atomic species within stellar atmospheres, allowing researchers to determine chemical compositions, temperatures, densities, velocities, and ages of distant cosmic structures with remarkable precision and reliability. Unlike photometric measurements that estimate galaxy properties based on brightness and color information alone, spectroscopic data provides unambiguous evidence about redshift values that directly translate into distance measurements and cosmic ages through well-established relationships between wavelength stretching and universal expansion rates. multiple research teams immediately began developing observational proposals designed to secure precious telescope time for follow-up studies using Webb's advanced spectrographic capabilities, recognizing that extraordinary claims about early galactic evolution would require extraordinary evidence before gaining acceptance from the broader astronomical community. The collaborative nature of modern astronomy ensured that verification efforts would involve independent groups using different analytical approaches, instrumental configurations, and theoretical frameworks to cross-check results and identify potential systematic errors that might have influenced initial interpretations of these mysterious objects. One particularly important alternative explanation suggested that some or all of these bright red sources might actually be active galactic nuclei or quasars rather than stellar populations, representing supermassive black holes actively consuming surrounding matter and producing intense electromagnetic radiation that could mimic the spectral signatures expected from massive galaxy systems. Quasars can appear deceptively similar to galaxies in low-resolution images, while actually being powered by fundamentally different physical processes involving gravitational accretion onto central black holes rather than distributed stellar formation throughout extended galactic structures. Distinguishing between these possibilities required careful analysis of spatial profiles, spectral line ratios, and variability characteristics that could reveal whether observed emissions originated from distributed stellar populations or concentrated accretion phenomena near massive black holes. The scientific community's measured response reflected decades of experience with astronomical discoveries that initially appeared revolutionary, but eventually proved to result from instrumental limitations, calibration uncertainties, or incomplete understanding of observational selection effects that can bias survey results toward unusual or extreme objects. This historical perspective encouraged healthy caution while maintaining openness to genuine discoveries that might challenge established theoretical frameworks, creating an intellectual environment where skepticism served to strengthen rather than suppress innovative scientific insights. Research teams began forming international collaborations that combined complementary expertise in observational techniques, theoretical modeling, and statistical analysis methods, recognizing that resolving these questions would require coordinated efforts drawing on diverse scientific perspectives and analytical approaches. The verification process also involved careful examination of survey methodology and sample selection criteria to ensure that these 6 objects represented genuine examples of early massive galaxies rather than statistical flukes or observational artifacts that might result from instrumental biases or data processing procedures. Scientists acknowledged that confirming the existence of impossible galaxies would necessitate fundamental revisions to cosmological models while potentially revealing new physics governing stellar formation and galactic assembly under primordial cosmic conditions that no longer exist anywhere in today's mature universe. The balance between excitement and caution reflected astronomy's commitment to empirical evidence as the ultimate arbiter of theoretical validity, ensuring that paradigm shifts occur through careful accumulation of observational support rather than premature acceptance of sensational claims that might eventually prove unfounded. This methodological approach protects scientific credibility while remaining sufficiently flexible to accommodate genuine discoveries that expand human understanding of cosmic processes operating on scales far beyond direct terrestrial experience, demonstrating how rigorous skepticism serves as foundation for reliable scientific progress, rather than obstacle to innovative thinking. What extraordinary cosmic beasts could emerge from Webb's deepest observations to make even the impossible galaxies discovered earlier seem modest by comparison? In late 2024, an international research team led by scientists at the University of Geneva unveiled their analysis of the FRESCO survey data, revealing 3 absolutely colossal galactic structures that pushed the boundaries of cosmic possibility even further beyond theoretical expectations than previous discoveries had dared to venture. The first reionization epoch. Spectroscopically complete observation survey utilized Webb's most sophisticated spectrographic instruments to conduct systematic measurements of galaxy masses, distances, and stellar formation rates during the universe's earliest accessible epochs, providing unprecedented precision in characterizing ancient cosmic architecture. These 3 newly identified titans earned the nickname Red Monsters from their distinctive crimson appearance in Webb's infrared images, a coloration resulting from enormous quantities of cosmic dust that absorb shorter wavelengths while allowing longer and infrared emissions to escape and eventually reach our sensitive detectors across billions of years of cosmic expansion. Each red monster contains stellar populations nearly matching the total mass of our contemporary Milky Way galaxy, representing an accumulation of matter that conventional models insisted should require multiple billions of years to assemble through gradual gravitational processes and steady stellar formation over extended cosmic timescales. What made these discoveries particularly shocking was their temporal location within cosmic history, existing during the first billion years after universal creation, when theoretical frameworks predicted that only modest proto-galactic fragments should be capable of surviving in the chaotic environment of the primordial cosmos. The FRESCO survey's advanced spectroscopic capabilities allowed researchers to measure precise redshift values that unambiguously placed these massive structures at cosmic distances corresponding to epochs when the universe was less than 10% of its current age, eliminating any possibility that these objects represented nearby galaxies masquerading as ancient systems through observational confusion or measurement error. Unlike photometric surveys that estimate galaxy properties through colour and brightness measurements alone, spectroscopic observations provide definitive evidence about stellar masses, chemical compositions, and formation histories through detailed analysis of absorption and emission lines produced by different atomic species within stellar atmospheres. The precision achieved by FRESCO observations exceeded previous spectroscopic studies by substantial margins, enabling confident identification of stellar population characteristics that revealed these red monsters had achieved their enormous masses through sustained periods of incredibly efficient star formation that converted available gas into luminous stellar systems at rates approaching theoretical maximum limits. Dr. Mengyuan Xiao, lead author of the groundbreaking study published in Nature magazine, emphasized how these findings fundamentally challenge existing paradigms about early cosmic evolution and the physical processes that govern galactic assembly during primordial epochs when environmental conditions differ dramatically from today's mature astronomical landscape. The research team included astronomers from institutions across multiple continents, reflecting the collaborative nature of modern astrophysics, where revolutionary discoveries emerge through careful coordination of diverse expertise in observational techniques, theoretical modelling, and advanced data analysis methodologies. What distinguished the red monsters from previously discovered impossible galaxies was their extreme efficiency in converting raw cosmic material into stellar populations, achieving star formation rates that approached or exceeded theoretical predictions for maximum possible productivity under any conceivable physical circumstances. These ancient galactic giants appeared to be operating like cosmic manufacturing centers, running at impossible efficiency levels, transforming primordial hydrogen and helium into complex stellar systems at rates that violated fundamental assumptions about feedback mechanisms that normally regulate and limit stellar birth processes in galactic environments. The dusty composition that gave these objects their characteristic red appearance also provided crucial insights into their formation histories, indicating that multiple generations of massive stars had already lived complete life cycles from birth through explosive death, distributing heavy elements throughout the galactic medium and creating the cosmic dust that now obscures much of their ongoing stellar formation activity. This chemical maturity suggested that red monsters had been actively forming stars for hundreds of millions of years before Webb observed them, implying that their assembly process began during cosmic epochs so early that they challenged fundamental assumptions about when gravitational collapse could first overcome thermal pressure and radiation, feedback to enable sustained stellar production in primordial galactic systems. How can cosmic factories operate with efficiency levels that defy every principle physicists thought governed the conversion of raw galactic material into luminous stellar systems? The red monsters distinguished themselves from all previously observed galactic structures through their unprecedented ability to transform available gas reservoirs into stellar populations at rates approaching twice the maximum efficiency that theoretical models suggested should be physically possible under any circumstances. While contemporary galaxies typically convert only 20% of their total gas content into stars over billion-year timescales, with the remaining 80% remaining as diffuse material that resists gravitational collapse due to thermal pressure and stellar feedback effects, these ancient titans achieved conversion rates exceeding 40 to 50% of available cosmic fuel. This represents a dramatic departure from established understanding of how stellar nurseries operate, suggesting that regulatory mechanisms which normally prevent runaway star formation either functioned with reduced effectiveness during primordial epochs, or perhaps operated according to completely different physical principles under environmental conditions that no longer exist anywhere in today's mature universe. Think of these galactic systems as manufacturing facilities designed to produce stars with assembly line efficiency that modern industrial engineers could only dream of achieving, where every process has been optimized to minimize waste and maximize productive output through mechanisms that somehow overcame the fundamental physical constraints that limit stellar birth rates in conventional cosmic environments. The heavy dust content that gives red monsters their distinctive crimson appearance in Webb's infrared images provides crucial evidence about their remarkable productivity, because cosmic dust forms only after multiple generations of massive stars have completed entire life cycles from initial collapse through nuclear burning phases to final explosive deaths that distribute processed heavy elements throughout surrounding galactic medium. This dusty composition indicates that these ancient systems had already experienced sustained periods of intensive stellar formation, lasting hundreds of millions of years before Webb captured their light, implying that their assembly processes began during cosmic epochs so early that conventional theory suggests insufficient time had elapsed for gravitational structures to organize themselves into such sophisticated configurations. The mature stellar populations revealed through spectroscopic analysis demonstrate that red monsters contain not only recently formed hot blue stars that characterize active star-forming regions, but also substantial numbers of older, cooler stellar types that require extended evolutionary timescales to develop their observed characteristics through gradual nuclear processing of hydrogen into helium and heavier elements. This age diversity within individual red monster systems suggests that stellar formation has been proceeding continuously rather than occurring in brief bursts separated by long quiescent periods. Maintaining consistent productivity over timescales that span significant fractions of early cosmic history when the universe was still developing its fundamental large-scale structure. The sustained rapid growth evidenced by these observations challenges basic assumptions about how feedback processes should regulate galactic development, because newly formed massive stars normally produce intense radiation and powerful stellar winds that heat surrounding gas to temperatures where thermal pressure prevents further gravitational collapse until the medium has time to cool and condense again. Under normal circumstances, this self-regulating behavior creates cyclical patterns of stellar birth and quiescence that prevent galaxies from consuming all available gas too quickly, preserving fuel for extended periods of steady production, rather than experiencing brief episodes of frantic activity followed by starvation and dormancy. Red monsters appear to have somehow bypassed or overcome these regulatory limitations, maintaining high-efficiency stellar production for extended periods without experiencing the negative feedback effects that normally throttle star formation rates in galactic environments where intense stellar radiation and mechanical energy input from supernovae create hostile conditions for continued gravitational collapse. The physical mechanisms responsible for this extraordinary efficiency remain mysterious, possibly involving enhanced gas cooling rates, reduced stellar feedback effectiveness, or entirely novel processes that operated under primordial cosmic conditions characterized by higher gas densities, different chemical compositions and environmental factors that have been fundamentally altered by billions of years of stellar processing and galactic evolution. What makes these discoveries particularly intriguing is their consistency across multiple independent red monster systems, suggesting that extreme stellar formation efficiency represented a characteristic feature of early cosmic environments rather than an isolated anomaly that might be explained through unusual local conditions or rare evolutionary pathways that occasionally produce exceptional galactic structures. The evidence points toward a systematic difference between primordial and contemporary star-forming processes, indicating that our understanding of stellar birth mechanisms may be incomplete when applied to cosmic epochs when the universe operated according to physical principles that modern observations cannot directly access through studies of nearby galactic systems that have been shaped by billions of years of subsequent evolution. What fundamental shifts in our cosmic worldview become necessary when empirical evidence consistently demonstrates that the primordial universe operated with capabilities far exceeding every theoretical prediction about early galactic development? The red monster's discoveries suggest that cosmic epochs preceding the formation of familiar astronomical structures were characterized by physical processes and environmental conditions that enabled matter, organization and stellar assembly to proceed with efficiency levels that challenge basic assumptions underlying decades of carefully constructed cosmological models. Rather than representing a complete overthrow of established scientific frameworks, these findings indicate that our understanding of early cosmic physics may be incomplete, missing crucial mechanisms or underestimating the effectiveness of processes that operated under pristine conditions before billions of years of stellar evolution fundamentally altered the composition and behavior of intergalactic medium throughout the observable universe. The implications extend far beyond simple adjustments to galactic formation timelines, suggesting that primordial cosmic environments possessed characteristics that enhanced gravitational collapse, accelerated chemical enrichment, or provided alternative pathways for rapid stellar assembly that no longer function in today's mature astronomical landscape, where heavy element contamination and accumulated stellar feedback have created regulatory mechanisms that limit star formation efficiency. Future observational campaigns will require unprecedented coordination between Webb's infrared capabilities and the Atacama Large Millimeter Array's radio astronomy expertise, combining complementary wavelength coverage to investigate the physical mechanisms responsible for red monster efficiency through detailed measurements of gas kinematics, temperature distributions, and chemical abundance patterns that might reveal the secrets of primordial stellar formation processes. These upcoming studies promise to expand sample sizes beyond the initial 3 red monsters, potentially revealing whether extreme efficiency represents a universal characteristic of early cosmic structures or a special phenomenon limited to particular environmental niches that existed during specific epochs of galactic evolution when conditions favored rapid matter organization into luminous stellar systems. The scientific excitement surrounding these discoveries reflects astronomy's perpetual tension between theoretical prediction and observational surprise, where nature repeatedly demonstrates its capacity to exceed human imagination and challenge even the most sophisticated attempts to model cosmic processes through mathematical frameworks based on incomplete knowledge of physical principles operating under extreme conditions. Paradigm-shifting findings like the red monsters illustrate how empirical science advances through cycles of hypothesis formation, observational testing, and theoretical revision that gradually refine human understanding of natural phenomena while revealing new layers of complexity that demand increasingly sophisticated explanatory models. The process of accommodating unexpected discoveries within existing scientific frameworks requires careful evaluation of which fundamental principles remain valid versus which assumptions may need modification or complete replacement, ensuring that revised theoretical models maintain consistency with established observational evidence while successfully explaining new phenomena that challenge previous understanding. What makes these cosmic evolution implications particularly fascinating is how they demonstrate that the universe's developmental history contains chapters we're only beginning to read, with each new observational capability revealing previously hidden aspects of cosmic architecture and galactic assembly processes that operated under conditions dramatically different from contemporary astrophysical environments. The enhanced stellar formation efficiency observed in red monsters might indicate that early cosmic gas possessed characteristics that facilitated rapid cooling and gravitational collapse, perhaps involving primordial magnetic field configurations, dark matter density distributions, or chemical composition differences that no longer exist in regions where billions of years of stellar processing have enriched the medium with heavy elements. Alternative explanations involve modified physics operating under extreme density and temperature conditions that characterized the early universe, possibly including enhanced gravitational effects, altered thermodynamic behavior, or novel feedback mechanisms that enabled sustained high-efficiency star formation without triggering the self-regulatory responses that limit contemporary stellar birth rates in galactic environments. These theoretical possibilities highlight how astronomical discoveries often reveal the limitations of extrapolating physical laws derived from terrestrial laboratory experiments and contemporary cosmic observations to extreme conditions that existed during primordial epochs when the universe operated according to principles we're still learning to understand through indirect observational evidence. The collaborative nature of modern astrophysics ensures that red monster studies will involve research teams spanning multiple continents and institutions, bringing together diverse expertise in observational astronomy, theoretical modelling, computational simulation, and statistical analysis techniques necessary for extracting maximum scientific value from Webb's unprecedented datasets while maintaining rigorous standards for verification and peer review. This international scientific cooperation reflects humanity's collective commitment to understanding cosmic origins and galactic evolution through patient sondes, accumulation of empirical evidence that gradually reveals the elegant complexity underlying apparent simplicity in natural processes operating on scales far beyond direct human experience or intuitive comprehension. How could delicate spiral structures resembling our own Milky Way possibly maintain their graceful architecture during cosmic epochs, when theoretical models predicted that violent galaxy collisions and chaotic environmental conditions should have dreaded such fragile formations before they could establish stable configurations? Webb's systematic surveys of distant cosmic regions revealed an absolutely staggering population of over 1,600 disc-shaped galaxies, displaying the characteristic spiral arm patterns, central bulges, and flattened morphologies that define modern galactic architecture. Yet these elegant structures existed when the universe had completed only a few billion years of its developmental timeline. This discovery represents perhaps the most comprehensive challenge yet mounted against established theories of galactic evolution, because spiral galaxies require precisely balanced gravitational dynamics, stable rotational patterns, and relatively peaceful environmental conditions to develop and maintain their distinctive spiral density wave patterns that organize stellar formation into the graceful curved arms we observe in contemporary cosmic neighborhood surveys. The theoretical expectation for early cosmic epochs was fundamentally different, predicting that primitive galactic systems should experience frequent violent mergers, gravitational disruptions, and turbulent gas dynamics that would prevent the emergence of organized spiral structures until much later stages of cosmic evolution, when the universe had matured sufficiently for gravitational interactions to become more gentle and predictable. Finding intact spiral galaxies in the primordial cosmos was analogous to discovering perfect snowflakes maintaining their intricate crystalline symmetry while being battered by hurricane-force winds, a phenomenon so unlikely that it challenges basic understanding of the physical processes governing both snowflake preservation and galactic structural stability under extreme environmental stress. The presence of these ancient spiral systems suggests that either the early universe was far more stable and organized than previously imagined, or that spiral galaxy formation mechanisms operate through processes more robust and resilient than theoretical models had predicted, based on studies of contemporary galactic interactions and merger simulations. What makes this discovery particularly revolutionary is the sheer abundance of well-formed spiral structures identified across multiple independent survey fields, indicating that organized disk galaxies represented a common rather than exceptional architectural solution during cosmic epochs when conventional wisdom insisted that only irregular, chaotic stellar aggregations should be capable of surviving in the turbulent primordial environment. The existence of these early spiral galaxies forces astronomers to completely reconsider fundamental assumptions about how long various galactic formation processes require to produce stable, organized structures from the chaotic initial conditions that characterized post-Big Bang cosmic development. Previous evolutionary models suggested that spiral galaxies like our Milky Way required approximately 10 billion years of gradual assembly, accretion, and dynamical relaxation to achieve their observed structural complexity, organizational sophistication, and chemical maturity through extended periods of steady stellar formation and peaceful gravitational evolution. Webb's observations demonstrate that similar levels of galactic organization were achieved much earlier in cosmic history, compressing what theorists believed should be extended developmental timelines into dramatically shorter periods, while somehow avoiding the destructive merger events that simulations predicted should characterize early cosmic epochs. The morphological diversity observed among these ancient spiral systems rivals that found in contemporary galactic surveys, including examples with prominent central bars, multiple spiral arm configurations, and varying degrees of central bulge prominence that suggest sophisticated internal dynamical processes were operating effectively during primordial cosmic conditions. This structural sophistication implies that fundamental galactic physics, including spiral density wave propagation, stellar orbital resonances, and gravitational torque mechanisms, were functioning essentially identically in early cosmic environments despite dramatically different background conditions involving higher matter densities, elevated merger rates, and primitive chemical compositions. The discovery timeline implications extend beyond individual galaxy formation to encompass broader questions about cosmic structure development, dark matter halo assembly, and environmental factors that influence whether gravitational collapse produces organized disk systems versus irregular stellar aggregations during different epochs of universal evolution. These findings suggest that the transition from chaotic post-Big Bang conditions to organized cosmic architecture occurred far more rapidly and efficiently than decades of theoretical work had predicted, indicating that nature possesses mechanisms for establishing galactic order under circumstances that human models struggle to reproduce through computational simulation of early cosmic dynamics. The statistical significance of detecting so many well-preserved spiral structures across multiple survey regions eliminates the possibility that these observations represent rare statistical flukes or observational selection effects that might bias surveys toward unusual objects while missing typical examples of early galactic populations. What invisible forces could possibly protect the gossamer-thin spiral arms of ancient galaxies from destruction while they navigated through cosmic environments that should have been filled with gravitational turbulence, massive dark matter fluctuations, and frequent catastrophic collisions between emerging stellar systems? Spiral arm structures represent some of the most delicate architectural features found anywhere in the cosmic landscape, consisting of density enhancement patterns that propagate through galactic disks like waves moving across the surface of a pond, organizing stellar formation into elegant curved configurations that require precisely balanced rotational dynamics to maintain their coherent appearance over extended periods. These graceful patterns emerge through complex interactions between gravitational forces, stellar orbital mechanics, and gas flow dynamics that can be easily disrupted by external perturbations, gravitational encounters with neighboring galaxies, or internal instabilities that develop when stellar masses become unevenly distributed throughout the galactic disk structure. The early universe was expected to represent perhaps the most hostile possible environment for maintaining such fragile organizational patterns, characterized by dramatically higher galaxy collision rates, intense radiation fields from active galactic nuclei, and chaotic matter distributions that had not yet settled into the relatively stable configurations observed in contemporary cosmic neighborhoods. Finding well-preserved spiral structures during these primordial epochs was comparable to discovering meticulously maintained formal gardens thriving in the middle of active construction zones where heavy machinery operates continuously, foundations are being excavated, and environmental conditions fluctuate wildly from moment to moment. Webb's extraordinary infrared resolution capabilities proved essential for revealing the hidden structural details of these ancient spiral systems because cosmic dust that accumulated during their extended star formation histories partially obscures their delicate architecture when observed through conventional optical wavelengths that cannot penetrate the intervening material effectively. The telescope's ability to peer through dusty veils using longer wavelength radiation enabled astronomers to map spiral arm patterns, central bulge configurations, and overall morphological characteristics with unprecedented clarity despite the enormous distances and substantial redshift effects that complicate observations of such remote galactic systems. What emerged from these detailed infrared surveys was compelling evidence that organized galactic architecture was not only possible but remarkably common during cosmic epochs when theoretical predictions suggested that spiral galaxy formation should be virtually impossible due to environmental factors that favored chaotic stellar aggregations over ordered disk structures. The prevalence of spiral patterns among early galactic populations indicates that fundamental processes governing disk galaxy evolution operated with surprising effectiveness under primordial conditions, somehow overcoming or bypassing the disruptive influences that computational models predicted should prevent stable spiral configurations from developing or persisting in young cosmic environments. This organizational success suggests that either the early universe was considerably more stable than previously imagined, or that spiral galaxy formation mechanisms possess greater resilience against environmental perturbations than decades of theoretical research had recognized through studies of contemporary galactic interactions and merger event simulations. The implications for early cosmic habitability are profound because spiral galaxies provide particularly favorable environments for planet formation and biological development through their ability to maintain stable, stellar populations in galactic regions with appropriate heavy element abundances, while avoiding the extreme radiation environments that characterize galactic centers and the element-poor conditions found in outer galactic regions. The presence of mature spiral structures during the universe's first few billion years suggests that potentially habitable planetary systems could have formed much earlier in cosmic history than previously thought possible, extending the available timeline for biological evolution and increasing the statistical likelihood that complex life forms might have developed in galactic environments that achieved chemical and dynamical maturity billions of years before our own solar system condensed from interstellar material. These ancient spiral galaxies also demonstrate that sophisticated gravitational engineering was operating effectively in primordial cosmic settings, creating organized stellar neighborhoods with predictable orbital patterns, regulated star soil, formation histories, and stable chemical evolution pathways that could support the gradual accumulation of heavy elements necessary for terrestrial planet formation and the complex organic chemistry associated with living systems. The discovery challenges fundamental assumptions about cosmic development timelines and suggests that the universe achieved architectural sophistication far earlier than conventional models predicted, opening possibilities for extended periods of galactic evolution during which multiple generations of stellar populations could have enriched planetary systems with the chemical diversity required for biological complexity to emerge and flourish in cosmic environments that combine structural stability with chemical richness through mechanisms we are only beginning to understand. What happens when 3 decades of carefully constructed theoretical frameworks encounter observational evidence so compelling that entire chapters of astronomical textbooks must be rewritten to accommodate nature's apparent indifference to human predictions about cosmic development? For more than 30 years, the astronomical community had developed increasingly sophisticated computer models, mathematical simulations, and theoretical paradigms that consistently predicted disk galaxies should represent extremely rare phenomena during early cosmic epochs, with most galactic systems existing as irregular, chaotic stellar congregations lacking the organized structure that characterizes contemporary spiral and elliptical configurations. These theoretical foundations rested upon solid physical principles, including hierarchical structure formation, dark matter halo assembly, gravitational merger dynamics, and stellar feedback processes that had been validated through countless observations of nearby galactic systems and extensively tested through computational simulations of cosmic evolution under various assumed initial conditions. The consensus among theoreticians was virtually unanimous regarding early galactic morphology, suggesting that violent merger events, turbulent gas dynamics, and unstable gravitational interactions should prevent the emergence of delicate disk structures until the universe had aged sufficiently for environmental conditions to become more conducive to organized architectural development through gradual accretion and peaceful evolutionary processes. Webb's systematic revelation of abundant ancient spiral populations represents one of the most dramatic paradigm shifts in modern astronomy, forcing researchers to confront the humbling reality that even their most sophisticated theoretical constructions may fail to capture essential aspects of how cosmic structures actually develop under conditions that differ substantially from contemporary astrophysical environments. The power of direct empirical observation to overturn established theoretical expectations demonstrates science's fundamental commitment to letting natural phenomena serve as the ultimate arbiter of validity, rather than allowing elegant mathematical models to dictate what should be possible in cosmic settings that exceed human intuitive understanding or computational capability. These discoveries highlight how astronomical instruments function as extensions of human sensory apparatus, revealing hidden aspects of cosmic reality that remain completely inaccessible to pure theoretical speculation, regardless of how mathematically sophisticated or computationally intensive such modeling efforts might become through advances in supercomputing technology and numerical simulation techniques. The process of theoretical revision necessitated by Webb's findings illustrates the dynamic relationship between observation and theory that characterizes healthy scientific progress, where unexpected empirical results force researchers to re-examine fundamental assumptions, identify overlooked physical processes, and develop more complete explanatory frameworks that successfully account for both established and newly discovered phenomena. What makes this particular paradigm shift especially significant is its scope, affecting not just specific details about galactic formation timelines, but fundamental concepts about cosmic structure development, environmental influences on morphological evolution, and the effectiveness of various physical mechanisms operating under primordial conditions that no longer exist anywhere in today's mature universe. The excitement within the astronomical community reflects both intellectual satisfaction at witnessing major theoretical advances and professional anticipation of the research opportunities that emerge when established models require substantial modification or complete replacement through systematic investigation of previously unknown cosmic processes. Rewriting astronomical textbooks involves far more than simply updating numerical values or adjusting timeline estimates, requiring comprehensive reconsideration of causal relationships, physical mechanisms, and environmental factors that influence how matter organizes itself into increasingly complex structures throughout cosmic history under conditions that span enormous ranges of density, temperature, and chemical composition. The humbling nature of these discoveries reminds astronomers that the universe consistently exceeds human expectations and challenges even the most carefully constructed attempts to predict cosmic behavior through theoretical modeling based on incomplete knowledge of physical principles operating under extreme conditions that cannot be replicated in terrestrial laboratories. This theoretical upheaval also demonstrates how scientific understanding advances through iterative cycles of hypothesis formation, observational testing, and conceptual refinement that gradually approach more accurate representations of natural phenomena, while revealing new layers of complexity that demand increasingly sophisticated explanatory models and analytical techniques. The collaborative response to Webb's paradigm-shifting observations involves research teams across multiple continents working to develop revised theoretical frameworks that can successfully explain early galactic abundance, morphological diversity, and structural sophistication, while maintaining consistency with the established physical laws and observational evidence from contemporary cosmic environments. Future theoretical development will require innovative approaches that combine improved computational modeling capabilities with enhanced understanding of primordial physics, environmental conditions, and formation mechanisms that enabled rapid galactic assembly under circumstances that modern simulations struggle to reproduce accurately through conventional approaches to cosmic structure evolution. What does it mean for the foundation of cosmological understanding when revolutionary discoveries expand rather than demolish the theoretical frameworks that have guided astronomical research for decades? The remarkable galaxies revealed by Webb's observations present a fascinating paradox where empirical evidence simultaneously challenges specific predictions while reinforcing the underlying mathematical and physical principles that form the backbone of modern cosmic evolution theory. Rather than shattering established cosmological models like a hammer striking glass, these discoveries function more like finding an unexpected room in a house you believed you knew completely, forcing you to revise your mental floor plan while recognizing that the fundamental architectural principles governing construction remain perfectly valid. The standard cosmological model, built upon decades of careful observational verification and theoretical refinement, possesses sufficient flexibility and robustness to accommodate these surprising findings through modifications and extensions, rather than requiring complete abandonment of frameworks that have successfully explained countless astronomical phenomena across vast ranges of cosmic scale and temporal evolution. What emerges from careful analysis of Webb's discoveries is compelling evidence that star formation processes operating under primordial cosmic conditions may have functioned with enhanced efficiency compared to contemporary mechanisms, possibly involving physical factors that no longer exist in today's mature universe, where billions of years of stellar processing have fundamentally altered environmental characteristics. The early cosmic environment differed dramatically from modern conditions in terms of gas composition, matter density distributions, radiation backgrounds, magnetic field configurations, and dark matter clustering patterns, creating circumstances where gravitational collapse and stellar assembly might proceed through pathways that contemporary observations cannot directly investigate through studies of nearby galactic systems. Enhanced stellar formation efficiency during primordial epochs could result from numerous physical mechanisms, including more effective gas cooling through primordial molecular hydrogen formation, reduced stellar feedback effectiveness due to different chemical compositions, enhanced gravitational focusing through higher background matter densities, or novel hydrodynamic processes that operated effectively only under specific environmental conditions that characterized the universe's youth. These modifications to existing theoretical frameworks demonstrate science's remarkable capacity for self-correction and adaptive growth when confronted with empirical evidence that exceeds expectations while remaining consistent with fundamental physical laws that govern cosmic behavior across all observable scales and temporal epochs. The process of accommodating unexpected discoveries within established scientific paradigms requires careful evaluation of which core principles remain, inviolate versus which specific implementation details may need adjustment to properly account for previously unknown or underestimated physical effects operating under extreme conditions. What makes this theoretical evolution particularly elegant is how it preserves the mathematical structure and observational foundations that have made cosmological modelling so successful, while expanding the range of phenomena that can be explained through enhanced understanding of how familiar physical processes operate under unfamiliar environmental circumstances. The robustness of scientific models becomes apparent when they demonstrate sufficient conceptual flexibility to incorporate surprising new findings without losing their predictive power or explanatory coherence, suggesting that theoretical frameworks possess deeper validity than might be apparent from their specific numerical predictions about particular cosmic phenomena. This adaptive capability reflects the hierarchical nature of scientific understanding, where fundamental principles like gravitational dynamics, thermodynamic behavior, and nuclear physics provide stable foundations that support increasingly detailed models of specific processes like galactic assembly, stellar formation, and chemical evolution that may require refinement as observational capabilities reveal previously hidden aspects of cosmic development. The implications extend beyond purely academic interest in galactic evolution to encompass broader questions about cosmic habitability timelines, chemical enrichment histories, and environmental conditions that might support the emergence of complex structures ranging from planetary systems to biological organisms capable of contemplating their own cosmic origins. Future theoretical development will likely focus on identifying the specific physical mechanisms responsible for enhanced early cosmic productivity, investigating whether similar processes might operate in extreme environments found elsewhere in the contemporary universe, and developing predictive frameworks that can successfully anticipate additional surprises as Webb continues revealing hidden aspects of cosmic architecture and evolutionary history. The ongoing dialogue between theoretical prediction and observational discovery exemplifies science's commitment to empirical validation while maintaining openness to natural phenomena that exceed human imagination, ensuring that cosmological understanding continues evolving toward increasingly accurate representations of cosmic reality, regardless of how those discoveries might challenge established expectations about universal development and galactic formation processes. Could the brilliant cores of some ancient galactic giants actually represent supermassive black holes masquerading as stellar populations, creating observational illusions that complicate our interpretation of early cosmic architecture and galactic mass measurements? Recent investigations have revealed that distinguishing between genuine stellar formation activity and energetic emissions from actively feeding central black holes presents one of the most challenging puzzles in contemporary extragalactic astronomy, particularly when studying distant objects whose light has been travelling toward Earth for billions of years while undergoing significant redshift modifications. The complex interplay between supermassive black hole accretion processes and distributed stellar formation creates electromagnetic signatures that can appear remarkably similar when observed through the limited resolution capabilities of even the most advanced astronomical instruments, leading to potential misidentification of physical mechanisms responsible for observed luminosity and apparent galactic mass characteristics. Quasars represent among the most energetic phenomena in the known universe, powered by matter spiraling into supermassive black holes at rates that can release energy equivalent to the total luminous output of entire galactic stellar populations, creating point sources that shine with intensities capable of outshining their host galaxies by substantial factors across multiple wavelength bands. When these incredibly bright accretion-powered sources exist within early galactic systems that also contain significant stellar populations, the combined emissions can create composite spectra that challenge traditional techniques for separating contributions from stellar nucleosynthesis versus gravitational energy release through black hole feeding processes operating at the galactic center. The detective work required to distinguish between these different physical mechanisms involves sophisticated spectroscopic analysis techniques that examine specific emission line ratios, spatial brightness distributions, temporal variability patterns, and polarization characteristics that provide diagnostic signatures capable of revealing whether observed radiation originates primarily from stellar atmospheres or from hot gas falling across black hole event horizons. Recent comprehensive studies utilizing Webb's unprecedented spectroscopic capabilities have begun revealing the nuanced reality that many early galactic systems likely contain both significant stellar populations and actively accreting central black holes, creating hybrid objects where traditional classification schemes based on contemporary galactic archetypes may prove inadequate for describing primordial cosmic architecture. This emerging understanding suggests that the relationship between supermassive black hole growth and stellar formation during early cosmic epochs involved feedback mechanisms that differed substantially from processes operating in today's mature galactic environments, possibly involving enhanced accretion rates, modified jet activities, or alternative energy coupling processes that influence the surrounding gas dynamics and stellar birth rates. The feedback effects, generated by actively growing black holes, can either suppress or enhance stellar formation depending on environmental conditions, energy deposition mechanisms, and timescales over which different processes operate, creating complex evolutionary scenarios where black hole activity alternately promotes or inhibits galactic assembly through mechanisms that remain incompletely understood even in contemporary cosmic settings. Ongoing observational campaigns designed to unravel these mysteries employ multiple complementary approaches, including high-resolution imaging that can spatially separate central point sources from extended stellar distributions, time domain monitoring that reveals variability signatures characteristic of accretion process, and multi-wavelength spectroscopy that identifies unique emission features associated with different physical processes operating within galactic environments. The self-correcting nature of scientific methodology becomes particularly apparent in these investigations, where initial discoveries based on limited observational data gradually yield to more sophisticated interpretations as additional evidence accumulates through systematic follow-up studies conducted with increasingly sensitive instruments and refined analytical techniques. What emerges from this ongoing detective work is a progressively more complete picture of early cosmic evolution, where supermassive black holes and stellar populations evolved together through symbiotic relationships that involved complex feedback loops, competitive resource utilization, and environmental modification processes that shaped both galactic architecture and central black hole characteristics over cosmic time. The implications extend beyond individual object classification to encompass broader questions about cosmic mass assembly, chemical enrichment histories, and energy balance mechanisms that governed galactic development during primordial epochs when physical conditions differed dramatically from contemporary astrophysical environments where billions of years of evolution have established equilibrium relationships between different galactic components. Future progress in resolving these fundamental questions will require continued technological advancement in observational capabilities, theoretical modeling sophistication, and computational simulation techniques capable of reproducing the complex multi-physics processes that govern interactions between gravity, hydrodynamics, radiation transport, and magnetic field effects operating simultaneously within evolving galactic systems across cosmic history. What tantalizing secrets might emerge as Webb continues its systematic exploration of cosmic history, potentially revealing galactic populations and evolutionary processes that dwarf even the revolutionary discoveries we've encountered so far? The initial spectroscopic follow-up campaigns have begun confirming many aspects of the original photometric discoveries, while simultaneously uncovering additional layers of complexity that demand even more sophisticated observational strategies and theoretical frameworks to fully understand the mechanisms governing early galactic assembly and stellar formation efficiency. The Atacama Large Millimeter Array represents Webb's most important observational partner in these investigations, providing complementary wavelength coverage that can penetrate cosmic dust more effectively than optical or near-infrared radiation, revealing the cold molecular gas reservoirs and ongoing star formation activity that remain hidden from direct detection through conventional astronomical techniques. ALMA's radio interferometric capabilities enable precise measurements of carbon monoxide, water vapor, and other molecular species that serve as tracers for the raw material from which new stars condense, allowing astronomers to investigate whether ancient galaxies possessed enhanced gas supplies, improved cooling mechanisms, or alternative chemical pathways that facilitated the rapid stellar formation rates inferred from Webb's luminosity and mass measurements. Expanding statistical samples beyond the initial handful of impossible galaxies requires systematic survey strategies that can efficiently identify candidate objects across much larger regions of sky while maintaining sufficient sensitivity to detect even the most distant examples of these remarkable cosmic structures during epochs when the universe was less than 1 billion years old. The coordination between multiple observational facilities represents a logistical challenge, requiring careful scheduling, data sharing protocols, and analytical standardization procedures that ensure different, instrumental approaches produce consistent results when applied to the same astronomical targets across various wavelength bands and temporal baselines. Webb's anticipated operational lifetime extends well beyond the minimum mission duration, potentially providing decades of continued observations that will systematically map early cosmic architecture with unprecedented detail while monitoring how theoretical understanding evolves through accumulation of empirical evidence from increasingly sophisticated observational campaigns and refined analytical methodologies. The prospect of additional discoveries looms large as survey completion percentages remain relatively modest despite the dramatic findings already achieved, suggesting that current results represent merely initial glimpses into cosmic phenomena that may prove even more remarkable as systematic exploration continues, revealing hidden populations of ancient galactic systems operating under physical conditions we're only beginning to comprehend. Each newly confirmed discovery generates cascades of follow-up questions that probe deeper into fundamental physics, environmental conditions, and evolutionary pathways that shaped cosmic development during epochs when matter organization proceeded through mechanisms that may differ substantially from processes governing contemporary galactic assembly and stellar formation in today's mature universe. The iterative nature of astronomical discovery ensures that answering existing questions inevitably reveals new mysteries requiring additional observational validation, theoretical development, and computational modeling capabilities that push scientific understanding toward increasingly complete representations of cosmic reality, while highlighting aspects of universal behavior that remain beyond current explanatory frameworks. Future observational campaigns will likely focus on characterizing chemical abundance patterns within ancient stellar populations, investigating spatial distributions of different galactic morphological types across cosmic epochs, and measuring precise star formation histories that can distinguish between various theoretical models for early cosmic evolution and primordial environmental conditions. The technological challenges involved in conducting these studies require continued advancement in detector sensitivity, spectroscopic resolution, image quality, and data processing algorithms that can extract maximum scientific information from observations of incredibly faint objects whose light has been traveling toward Earth since cosmic epochs, when fundamental physical processes operated under conditions that no longer exist anywhere in the observable universe. Collaborative efforts between observational astronomers, theoretical modelers, and computational specialists will prove essential for developing comprehensive understanding of how Webb's discoveries fit within broader frameworks of cosmic structure formation, dark matter physics, and primordial nucleosynthesis that collectively determine how matter evolves from smooth post-Big Bang distributions into the complex hierarchical architecture characterizing today's cosmic landscape. The excitement within the astronomical community reflects recognition that we may be witnessing one of those rare historical moments when observational capabilities advance sufficiently to reveal entirely new categories of cosmic phenomena that challenge established paradigms while opening research directions that will occupy multiple generations of scientists working to understand implications for fundamental physics, cosmic habitability, and the ultimate fate of universal development through continued expansion and gravitational evolution over cosmic timescales that dwarf human comprehension, yet remain accessible through patient accumulation of electromagnetic information carried by photons that began their journeys when the cosmos was young. What profound comfort can we find in recognizing that the universe possesses an inexhaustible capacity for surprising even our most sophisticated attempts to predict its behaviour and understand its deepest mysteries. Throughout human history, each advancement in observational technology has consistently revealed cosmic phenomena that exceed our wildest imagination, demonstrating that reality operates on scales of complexity, beauty, and organizational sophistication that dwarf even the most creative theoretical speculation about how natural processes might function under extreme conditions. The cosmos behaves like an infinite library containing countless volumes we haven't yet opened, each chapter revealing new aspects of cosmic architecture and evolutionary processes that challenge us to expand our conceptual frameworks, while simultaneously inspiring deeper appreciation for the elegant mathematical principles underlying apparent chaos and complexity. There's something deeply reassuring about living in a universe that consistently refuses to be completely understood or fully predicted, ensuring that future generations will inherit mysteries just as profound as those that captivate contemporary astronomers and challenge them to develop increasingly sophisticated tools for exploring cosmic phenomena that remain beyond current observational reach. The humbling nature of astronomical discovery creates a beautiful paradox where increased knowledge simultaneously expands our awareness of how much remains unknown, fostering intellectual humility that enhances rather than diminishes our sense of wonder about natural processes operating on scales ranging from quantum mechanical interactions to cosmic structure formation across billions of years of universal evolution. Scientific understanding functions as a lens that clarifies cosmic beauty rather than explaining it away, revealing intricate relationships between fundamental forces, matter organization, and energy transformation that demonstrate how elegantly physical laws create order from apparent randomness through mechanisms we're gradually learning to appreciate through patient observation and careful analysis. The ongoing human journey of cosmic exploration represents one of our species' most noble endeavours, driven by curiosity about our place in the universal story and motivated by recognition that understanding cosmic processes enriches our appreciation for the remarkable circumstances that enabled life to emerge and develop consciousness, capable of contemplating its own origins. Each generation of astronomers builds upon previous discoveries while developing new questions that guide future research directions, ensuring that cosmic exploration remains an active dialogue between human intellect and natural phenomena, rather than a passive accumulation of facts about distant objects and ancient events. Webb's revolutionary discoveries demonstrate how observational breakthroughs can simultaneously answer long-standing questions while revealing entirely new categories of cosmic mystery that demand fresh theoretical approaches and innovative observational strategies to investigate phenomena that exceed the explanatory power of existing scientific frameworks. The surprise factor inherent in major astronomical discoveries serves as a constant reminder that the universe operates according to principles more sophisticated than any single theoretical model can encompass, suggesting that cosmic reality possesses depths of complexity that will continue challenging human understanding for generations yet to come. What makes these surprises particularly valuable is how they force us to question assumptions that may have gone unchallenged for decades, leading to conceptual breakthroughs that enhance our ability to recognize patterns, predict behavior, and appreciate connections between seemingly unrelated phenomena operating across vast ranges of spatial and temporal scale. The emotional dimension of cosmic discovery involves not just intellectual satisfaction, but genuine awe at recognizing our participation in a universe capable of creating structures of stunning beauty and functional sophistication through purely natural processes, operating without conscious design or deliberate intention over cosmic timescales that dwarf human historical experience. Scientific wonder emerges from understanding rather than ignorance, growing stronger as we develop deeper appreciation for the mathematical elegance, physical consistency, and evolutionary creativity that characterize cosmic development from its earliest moments through contemporary epochs when complex organisms can study their own cosmic heritage. The universe's capacity for surprise reflects its fundamental nature as a dynamic system, where simple rules operating under diverse conditions can produce outcomes that exceed predictive capabilities while remaining consistent with underlying physical principles that govern behavior across all observable scales and developmental stages. Future cosmic exploration will undoubtedly reveal additional surprises that challenge current theoretical frameworks, while inspiring new generations of scientists to push observational boundaries and develop conceptual tools adequate for understanding phenomena that currently lie beyond human imagination, yet operate according to discoverable natural laws accessible through patient empirical investigation. The comfort we derive from cosmic mystery stems from recognition that living in a completely understood universe would eliminate the intellectual adventure that drives scientific progress and reduces opportunities for experiencing the profound satisfaction that comes from participating in humanity's gradual expansion of knowledge about natural phenomena, operating on scales that transcend individual human experience while remaining connected to our daily existence through shared participation in cosmic evolutionary processes. How does it change our perspective on existence to realize that the impossible galaxies Webb discovered represent our own cosmic ancestry, stellar communities that were already ancient when our solar system was nothing more than a diffuse cloud of interstellar dust waiting to collapse under gravitational influence? These primordial galactic giants were busily converting hydrogen and helium into the heavier elements that would eventually become incorporated into planetary systems like ours, creating carbon for organic molecules, oxygen for water and atmospheres, silicon for rocky surfaces, and iron for planetary cores through nuclear fusion processes operating within stellar furnaces that burned brilliantly when the universe was young. The extraordinary journey from those first stellar beacons to human consciousness represents perhaps the most remarkable transformation in cosmic history, spanning billions of years during which matter organized itself into increasingly complex structures through gravitational assembly, chemical evolution, biological development, and ultimately neurological sophistication capable of studying the very processes that created the conditions necessary for its own emergence. Understanding deep time provides a profound sense of connection to universal development that transcends individual human lifespans and cultural boundaries, revealing how contemporary existence represents the current chapter in an ongoing cosmic story that began with quantum fluctuations during cosmic inflation and continues through galactic mergers, stellar evolution, planetary formation, and biological complexity that may eventually spread throughout the observable universe. The patience exhibited by cosmic evolution becomes particularly apparent when we consider how billions of years of gradual change were required to transform the universe from a relatively simple collection of hydrogen and helium atoms into the intricate ecosystem of galaxies, stars, planets, and living organisms that characterizes today's cosmic landscape despite the rapid galactic assembly processes Webb discovered during primordial epochs. Even those surprisingly efficient early phases of cosmic development occurred over hundreds of millions of years, timescales that dwarf human historical experience yet represent mere moments compared to the extended periods required for stellar nucleosynthesis to create sufficient heavy element abundances for terrestrial planet formation and the subsequent chemical evolution that enabled life to emerge from non-living matter. Our remarkable privilege as conscious observers, capable of witnessing cosmic history through advanced technological instruments, represents an almost unimaginably unlikely convergence of circumstances where matter has organized itself sufficiently to study its own origins, development, and ultimate destiny through electromagnetic radiation that carries information across billions of years of space and time. The photons entering Webb's detectors from ancient galaxies began their journeys when the universe contained no rocky planets, no organic chemistry, and no possibility for biological complexity, yet through patient cosmic evolution those same physical processes eventually created planetary environments where complex molecules could assemble into self-replicating systems capable of developing consciousness and building instruments sophisticated enough to capture those ancient photons and interpret their scientific significance. We exist at a unique moment in cosmic history when technological capabilities have advanced sufficiently to reveal the universe's developmental timeline, while the cosmic expansion rate remains slow enough that distant galaxies haven't yet disappeared beyond observational reach, providing a narrow temporal window during which conscious beings can study cosmic evolution and appreciate their connection to universal processes operating on scales that exceed individual comprehension. The continuing story that we participate in extends far beyond current human civilization to encompass galactic mergers that will reshape our cosmic neighborhood, stellar evolution that will alter the composition of interstellar space, planetary system formation that may create new habitable environments, and potentially biological development that could produce forms of consciousness we can't currently imagine operating within cosmic contexts we haven't yet discovered. Each Webb observation connects us directly to cosmic ancestry through electromagnetic messengers that departed their sources during epochs when our galactic neighbourhood was still assembling from smaller gravitational structures, carrying information about physical conditions, chemical compositions, and evolutionary processes that contributed to creating the environment within which our solar system eventually formed and biological complexity could develop. The temporal perspective provided by studying ancient galaxies reminds us that human existence represents just one brief phase in an ongoing cosmic experiment where matter continues exploring new possibilities for organization, complexity, and perhaps consciousness through processes that operate according to natural laws we're gradually learning to understand despite their operation on scales that challenge human intuition and temporal perception. Future cosmic evolution will undoubtedly produce developments as remarkable as the transition from primordial galactic assembly to conscious observation, suggesting that our current understanding represents an intermediate stage in cosmic development rather than its culmination, ensuring that the universe will continue surprising and inspiring whatever forms of consciousness emerge to study its ongoing transformation throughout deep future epochs that extend far beyond current astronomical prediction capabilities. What gentle truths about our cosmic home can we carry with us as we conclude this unhurried journey through some of the most remarkable discoveries in astronomical history? Tonight we've wandered together through revelations that have quietly revolutionized our understanding of cosmic development, from those 6 impossible galactic giants that first caught astronomers by surprise to the dusty red monsters that challenged every assumption about stellar formation efficiency, and finally to the thousands of ancient spiral galaxies that maintained their delicate architecture during epochs when chaos should have reigned supreme. These discoveries share a common thread that speaks to something profoundly comforting about the universe we inhabit, revealing a cosmos far more creative, organized, and capable than our most optimistic theories had dared to suggest during decades of careful theoretical development and observational investigation. There's a beautiful serenity in recognizing that we live within a universe that consistently exceeds human expectations, not through violence or destruction, but through elegant demonstrations of natural processes operating with sophistication that surpasses our current ability to fully comprehend or predict their outcomes. The knowledge that cosmic evolution proceeded through pathways more efficient and architecturally sophisticated than scientists had imagined provides a sense of living within a reality that possesses hidden depths of creativity and organizational capability waiting to be discovered through patient observation and thoughtful analysis. As you contemplate tonight's sky, perhaps you'll find yourself looking up with renewed appreciation for the complex history embedded within every point of starlight, knowing that some of those distant photons departed their sources when the universe was creating galactic masterpieces through processes we're only beginning to understand and appreciate. The ancient galaxies we've explored together exist not as abstract scientific concepts, but as genuine cosmic communities that were already thriving when our own galactic neighbourhood was still assembling from primordial material, suggesting that stellar civilizations and planetary systems may have had billions of additional years to develop. Complexity and perhaps consciousness in cosmic environments that achieved chemical and gravitational maturity far earlier than previously thought possible. Webb's discoveries invite us to expand our temporal perspective beyond human scales to encompass cosmic development over billions of years, fostering a kind of intellectual humility that enhances rather than diminishes wonder about our place within universal processes that continue operating according to natural laws we're gradually learning to recognize and appreciate. The peaceful contemplation that emerges from understanding cosmic timescales provides perspective on temporary concerns, while connecting us to ongoing processes that link our current existence to the most fundamental aspects of universal development and stellar evolution. Tonight's exploration demonstrates how scientific discovery can serve as a pathway toward deeper appreciation for natural beauty and cosmic connectivity, rather than reducing mystery to mere mechanical processes, revealing layers of complexity and elegance that inspire continued wonder about phenomena operating beyond direct human experience. The comfort we derive from these cosmic insights stems partly from recognizing that despite technological advancement and increased understanding, the universe retains inexhaustible capacity for surprising us with revelations that challenge assumptions while expanding possibilities for continued discovery and intellectual adventure. As you settle into whatever restful activities await you this evening, carry with you the knowledge that cosmic evolution continues its patient work of creating increasingly complex and beautiful structures through processes that operate with mathematical precision, yet produce outcomes that consistently exceed human imagination and theoretical prediction. The galaxies we've discussed tonight remind us that cosmic history extends far beyond individual human experience while remaining intimately connected to our daily existence through shared participation in ongoing universal development that links quantum mechanical processes to galactic architecture through elegant physical relationships. There's no urgency to grasp every detail or solve every cosmic puzzle we've encountered. Instead, we can simply appreciate having shared in humanity's gradual expansion of knowledge about natural phenomena, while recognizing that future discoveries will undoubtedly reveal additional aspects of cosmic beauty and complexity that exceed current understanding. Whether tonight finds you drifting towards sleep, engaging in quiet evening activities, or simply enjoying the peaceful satisfaction that comes from learning something new about our remarkable cosmic heritage, may your rest be enhanced by awareness that you're part of an ongoing story that connects conscious observation to universal processes operating across scales that span from subatomic interactions to galactic evolution over billions of years of cosmic time.